Yep. So the streaming is live, but it's the waiting page. We are not live. You should also hopefully be able to get the audio now.
Okay, just give me a
Okay.
second. Let you
Checking
know
the
when
audio.
it's. Okay, I can see this. Yeah.
Perfect.
Okay, just let me know whenever you're ready.
Yes, we should be live.
Okay. So thank you everyone for joining us for the February iteration of Theory Matters. So I'm Amit Alok and my partner in crime is Shank. We're both here. And this time we have the pleasure of inviting Rajat Mittal from IIT Kanpur. So Rajat is somebody I just got to know. Yeah, so we just got to know him when I just joined Kharagpur, so it's been a year back since, and it's of course a long time since the lockdown kicked in. But Rajat is going to talk about aspects of Fourier analysis on Boolean cube. Specifically, he's going to talk about the relation between rank and sparsity for Boolean functions and specific results to Chang's lemma. So Rajat has been interested widely in quantum computing and Boolean analysis, Fourier analysis of Boolean functions and computational number theory. He's currently at IIT Kanpur as an assistant professor. And prior to that, he was an undergraduate at IIT Bombay and did his PhD at Rutgers, after which he spent some time at the Institute for Quantum Computing in Waterloo. So we're looking forward to talk, and I'm sure, based on the abstract, I'm sure many of you are as well. So I'll share the space to Rajat now. So thank you, Rajat. Please go ahead when you're ready.
Thanks, Amitabh. Thanks, Ashan. Thanks both of you for inviting me. I hope I can do a good job of explaining this result. Can you see my slide and hear me clearly?
Yes. Yeah. Okay.
Great. This, as Amitabh already said.
Oh, Rajat, sorry to interrupt. So yeah, people who so you've joined. So if you have any doubts, please feel free to unmute and interrupt Rajat for the question. Okay, it may be helpful to others as well.
Right.
Thank you.
Right. Thanks. So yeah, so today I'm going to talk about, as Amit Alok already mentioned, I'm going to talk about Fourier analysis on Boolean hypercube, specifically the relationship between the rank and sparsity of a Boolean function. I will introduce these terms, and again, please feel free to interrupt me if things are not clear. This is a joint work with Saurav and Manasvi, both from ISI, Nikhil Mande, Tulsi, and Swagato. Swagato is at IIT KGP. He is in the audience. So let's start. I want to say that there are many more things in the paper. I'm going to concentrate on a very specific part of the paper, which is the relationship between rank and sparsity. Fourier analysis, I'm sure almost all of you have heard of it, have seen it. Very, very useful in diverse applications, signal processing, physics, and even when you restrict Fourier analysis to different groups, it has found numerous applications in number theory. Today, we are going to see that what kind of Fourier analysis we are interested in when we talk to computer scientists. As a computer scientist, there is a particular Fourier transform we are really interested in, which is the Fourier transform on Boolean hypercube. As computer scientists, we like bits, or we like things which take values true and false, +1, -1, yes, no, whatever you want to say. And we want to study these kind of functions. Functions whose domain is +-1. And to start with, let's say, they can give us any real value. In general, Fourier transform takes a function from some group to real number or complex number and gives you a representation in a different basis. It is going to be similar for the Boolean hypercube. A function like this can be represented in these terms. Here, chi sx are parity functions. And this f at s is going to be the Fourier coefficient. Yeah, so you can see my complete screen, right? Or this meet.google.com is interfering? Should I hide it?
I can see the whole screen actually.
It is the whole screen. Right. So a very simple statement for us to start with would be that any function from -1, 1 to n to real numbers can be written as a polynomial. A very specific polynomial. Notice here, if you look at these parities, these are all polynomials with individual degree at most 1. Such polynomials are actually called multilinear polynomials. They are linear in individual coordinates. The proof of this thing is not very hard. Let's not worry about it. Obviously, polynomials can be changed to linear polynomials because our domain is -1, 1. That means xi square is equal to 1. Wherever I have higher powers of xi square, I can just replace them by 1 or xi and just make it linear. So it should not come to you as a surprise that every polynomial can be, when we talk about a function, the corresponding polynomial can be made multilinear. It turns out that every function can be written as a polynomial in this way. And that's the statement of Fourier transform. These, if you want to go into detail, these parities are actually characters and they satisfy some nice property, but let's not worry about that. At this point, remember that every function from -1, 1 to the n to real numbers can be written as this multilinear polynomial. This thing is unique. I will come to that, but yeah, this is the statement for Boolean hypercube. It turns out it has numerous applications, especially in computer science, property testing, coding theory, complexity theory, so on and so forth. But you know, we are in Theory Matters seminar series. So let me just skip all this, say this has many applications, and talk about the mathematical result, what we are going to do. So I am not going to spend more time on selling it, saying that, oh, Fourier analysis is great. It is. There are books written about it. There are surveys and all. But let's see what kind of cool mathematics we can do on this. Let's go slightly deeper into what happened there, right? I said that every function can be written as a multilinear polynomial, right? Any questions? Okay. So yeah, so I have a Boolean function. It can be written as this polynomial, right? Fx is equal to summation f at s chi sx. Here, f at s were the Fourier coefficients, and chi sx is just a way to write a monomial. This is basically a polynomial. F at s are the coefficients, and chi sx is the monomial which is captured. This is what I am saying. And if you think about it, you can actually come up with the value of f at s. Actually, there is a very clear way to see what we are doing, especially when we are just talking about functions which take real value. It turns out that these chi sx's, right? Okay, let me say this. How would you specify a function from -1, 1 to the n to r? This is specified by 2 to the power n real numbers, right? I can view any f as a vector in this vector space, r to the power 2 to the n. Make sense? In this vector space, my parity functions actually form an orthonormal basis. I have put orthonormal in the quotes because you have to worry about normalization. If you look at the usual definition of norm, Euclidean norm, then chi sx is not normalized, but you can change the inner product slightly and you can think of them as orthonormal basis, or you can say that they are orthogonal basis. But the point stays that since chi sx is an orthonormal or orthogonal basis, you can write any function as a linear combination of these chi sx's. So this equation is basically a basis change equation. I had my function representation in the point basis where I give its value on every coordinate, right? That's one way to represent my function. What is its value on 1, 1, 1, 1, 1? What is its value on -1, 1, -1, 1, 1, 1, 1, 1, -1, -1, -1, and so on? That's one way to give the value of function. Other way is to do a basis transform on this vector space, r to the 2 to the power n, and that is this Fourier analysis. It is not just that, it is much more than that, but let's start with that. At this point, Fourier analysis is just a basis change to a nice basis, the basis of parities, the basis of these monomials. That way, you can kind of see many of the things which are shown for the Fourier analysis. Great. Till this point, let's notice that every function can be viewed as a vector in r to the power 2 to the n, and then since these form an orthonormal basis, I can change the basis and write my function in a new basis of parities. Then my coordinates will be this fx. And this basis change has been useful in many scenarios. Let's go further. Let's take actually a few examples. So constant function, if I say that my function value is the same at every point, then its polynomial representation should be just c times 1 plus 0 times x1 plus 0 times x2, so on. So every other coefficient except the coefficient of the of s is equal to 5 would be 0. Does that make sense? This is called the simplest function to take the Fourier transform of. I'm just trying to give some Fourier transform so that you become familiar with it. So is it too simple? Should I go ahead?
Yeah, please do.
Should I go? So no questions, right? This is fine, right?
Yeah, none from me, please.
This is. I can take parity function on some subset of my inputs. If my input were x1, x2, xn, I can say that my function is a parity on, let's say, x1, x2, x3. Then my fx should be just x1, x2, x3. This is the polynomial representation for my parity on x1, x2, x3. Again, in this case, only one Fourier coefficient will be non-zero, everything else will be 0. Again, a very, very simple case. Let's take the first non-trivial case, end of x. Right? In this case, I'm changing from 0, 1 to -1, 1. So this definition might seem slightly different, but just notice that it is -1 on just one value. So -1 is true. It is true when everything is true, false otherwise. So -1 is true and 1 is false. If you are familiar with that notion of AND function, then this is the AND function. And by the previous formula on of figuring out the coefficients, remember that this was our formula. Then you will get the values of the Fourier coefficients of AND function. You can figure out what are the coefficients of the monomials when I represent AND as a polynomial.
Rajat, I had one question here. So when you define parity as via subset, right? So you give a subset, parity will be outputting 1 only if that subset occurs.
Right. So you are right. So generally, when I talk about parity, ideally it is a parity of all n bits, right? Parity of x1, x2, xn. But here I am talking about a class of parities, parity functions, where any parity on any subset is also allowed. Even for that, it is easy to see the Fourier transform.
Okay. And the way you're defining AND, just confirm this is the case. You're saying if the x vector is all -1s, the AND is given as -1. And any other case, okay, fine.
It's yeah. So yeah, in this -1 domain, -1 is true and 1 is false. So that
okay.
Right. So then it will agree with the normal notion of AND function. And the point is you can even figure out the Fourier coefficients here. I might be slightly off by a constant, and actually, like a true complexity theorist, I will skip all constants in my talk later. I will just write equal when I mean it is theta or O or omega, and I will let you figure out what should be the right notation there. I will not worry about it. I will just ignore all the constants and it won't lose anything. So don't worry about it, right? Right. So you can
silly question here. So when we define, why are we specifically going from 0, 1 to instead of going 0, 1 to the end, why are we going -1 plus 1 to the end? Is there a reason for that?
It just makes it nicer. You can have a Fourier transform with 0, 1, then your basis would be this x1 plus x2 and so on. So that will be this polynomial thing comes if you take the functions to be input to be -1, 1.
Okay.
So it's easier to do Fourier analysis with -1, 1. But yeah, those are equivalent, right? Even on 0, 1, you can do all the same things. The notation will be slightly more complex. Okay. Okay. So yeah, and even this formula, actually, you don't need to remember this. You remember that Fourier transform was a basis change. This is actually just the inner product, normalized inner product between f and chi s. That's why this formula comes, right? If I want to represent a function in some orthonormal basis, what is the coefficient on one particular element of that orthonormal basis? You will just take the inner product with that. You will just take the projection on that. This is what I am doing in this formula. This is just the inner product or dot product between normalized dot product between f and chi s. By notation, that's clear. I'm normalizing it by 1 to the power 1 by 2 to the power n because chi s is not a unit vector. But essentially, this is it. Whatever I am doing till now is simple basis change in this vector space. Nothing more than that. Okay, all this is fine. Let's make the things interesting. I'm going to say now, suppose my functions are restricted to take only values -1 and 1. Not just the input, but the output is also Boolean. Such functions are called Boolean functions. The restriction is simple. Remember, if the range was R, when I had functions from -1, 1 to n to R, then I had a simple polynomial representation. I had a new basis. You can convert every function into a Fourier transform, and given a Fourier transform, you can convert it back into a function. Now let me talk about this special class of functions where my range is -1, 1. It is a specific range. Question is, how does that become special, or how does that restriction manifest itself in the Fourier transform? This set of Fourier coefficients should become special, right? I'm saying that my range is -1, 1. That means my Fourier coefficient should also satisfy some nice properties. And that is what many of us do. We want to try out and figure out structure in this f at s's. When f at s's correspond to a Boolean function. That means the range is -1, 1. This is like the more philosophical picture of this field. To start with, if I make the function Boolean, what can I say about Fourier coefficients? There are simple things which are not very deep. They're very, very useful, like Parseval's theorem. This is basically saying that in both the bases, the norm remains the same. This is one theorem. Then you can even say that your f at s is a multiple of 1 by 2 to the power n. Many things, there are few small things which come very quickly about f at s, which are very, very useful. Now, let me put the this what I call the useless slide, right? In any presentation, this is going to be the outline here, right? You will introduce the question, you will talk about your result, then explain the proof, and then conclude. Let's take this thing as a time for a break, and let me ask you if there are any questions about the setting. Till now, what we have seen is that we have Fourier transform, and you want to figure out how is the Fourier transform, or how are the Fourier coefficients special when I'm talking about these special functions. That means Boolean functions. So any problems with the setting?
So maybe one sort of generic question. So what kind of properties do people look for, like computer scientists look for?
I will show. I will give you a good example of one such property, right? So in general, like if you talk about property testing, one of the thing is that suppose your Fourier coefficients, Fourier spectrum is sparse. That means very few things are non-zero.
Yes.
What can you say? What does it? Because in general, for when the range is R, then sparsity doesn't tell you anything. Every sparse function is a function whose range is R.
True.
But then when you talk about Boolean functions, sparsity imposes a lot of restrictions. So can you say that, oh, is it easy to learn?
So again, when you talk about sparse Boolean functions, you mean that the number of minus ones is small. Is that it?
No. I'm saying sparse in the Fourier domain. That means
Okay,
the number
fine.
of Fourier coefficients.
Okay.
Number of Fourier coefficients which are non-zero are small.
Okay.
So I'm talking about Fourier sparsity. But yeah, even that could be even that is also an important parameter.
Sure.
What are the number of minus ones, right? We call it the weight of the function.
Correct.
Yeah.
The weight of the function.
Even that is, yeah.
Yeah, because it's not the same sort of the sparsity. I mean, in the whatever time domain, it's not the same notion of sparsity since the function values are only allowed to take +1, -1, so something like an uncertainty principle is kind of meaningless here, I guess.
There is an uncertainty principle.
Oh, for Boolean functions as well?
Yes. I will use it.
Oh, okay.
So, yeah.
Just one question, this is Lalita. So how is this Boolean function representation? Is it related to the, I mean, I forget if it is Walsh-Hadamard transform or something like that.
So Fourier analysis. So I'm doing this on z to the power n, right? The group is z to the power n.
Okay.
The Fourier transform on z to the power n is the Hadamard transform.
Okay.
So right. So that is so if I want to give you the matrix which converts from one side to another, that would be this Hadamard transform.
Okay. Thanks.
Okay. Now in this setting, now let's talk about what is the question in this framework. So what structure do we want to figure out? The first thing I already mentioned to Sanyal that we can one of the interesting quantities is the support of F, which is all the sets whose Fourier coefficient is non-zero. Remember, this was the function, right? This was the representation of the function, and now I'm looking at sets whose Fourier coefficient is non-zero. To remind you, when I said that the function is sparse, I meant that the size of the support is small. That would be my definition of Fourier sparsity. And then again, the question could be, we can ask if F is Boolean, it should impose a lot of restrictions on support of F. Can we figure out these restrictions? And we will see one such in this result. And another interesting thing is that till now we were talking about this R to the vector space of R to the power 2 to the n. But now when we talk about support of F, actually the support of F in itself is a vector space. Would anyone would like to take a guess? What is that vector space? If I look at parities, if I look at all the subsets of, let's say, n-sized, all subsets of n-sized set, I can think of that as a vector space, all Boolean strings of length n. And I can impose a structure on that. What kind of vector space would that be? Okay, so it is going to be f2 to the power n. Right, so I can think of these subsets as elements of f2 to the power n, and then I can add them, because I can add them, I can do all the operations on them as possible. Is this something which I need to explain more, or this is fine? So think of.
So yeah, so what are the operations on this vector space that you're learning?
So the constants are just 0 and 1, right?
Correct.
So basically you just add, right? And if you write the indicator vector as 0, 1, 0, 1, something like that, let's say this is one subset, then you can take the XOR of coordinate wise things, right? That would be the addition.
Sure.
So addition in F2.
Okay, so that is symmetric difference of.
Correct. Right. That would be the addition here.
Okay.
And you can see that corresponds to multiplying the chi-s axis, right?
Yeah.
That is exactly equivalent to that.
Correct.
So when I multiply the parities there, the corresponding subsets get added up in this vector space f2 to the power n.
Sure.
Right. So x1, x2, x2, x3.
Mm-hmm.
This corresponds to 1, 2. This corresponds to 2, 3. If I apply the group operation or F2 operation on that, I will get x1, x3, which is, as you said, the symmetric difference.
Okay.
So x2, obviously x2 square is 1, right?
Yeah.
Wherein minus 1, 1. Cool. Right. Once we view it as a vector space once we view the sets as vector space over f to the power n, we can define two quantities for the support. One is the sparsity, the number of elements in support of f, and the rank, which is the dimension of the span of support of f. Right? So I'm just going to call them sparsity and rank, but probably the correct term would be Fourier sparsity and Fourier rank, for so as to not confuse with any other rank and any other sparsity. But I'm talking about Fourier analysis, then I will skip the text before this. I will not say Fourier sparsity, I will not say Fourier rank. This is sparsity of f and rank of f for us. Sparsity is the number of non-zero coefficients, and rank is the dimension of the span of the support of f. That sounds okay. Right. For example, if the support was full, that means every Fourier coefficient was non-zero, then the dimension would be so if support of f is all possible subsets of size n, then rank of f would be, any guesses? It would be just a complete and the rank would be n, right? Because this.
So I guess maybe one way to sort of view things is that, so this is the Fourier transform is basically a map from f2 to the end to r, right? And so the sparsity is, of course, basically just the support, the standard support, and that gives you a set of vectors, and rank is just the dimension of the span of these vectors.
Exactly. Right? So you now, whenever I talk about rank, you take the Fourier coefficient, you look at the support, look at each element of the support as vectors.
Yeah.
Right? And then you can talk about dimension of the span of those set of vectors. Right? Okay. Another simple exercise. What would be the rank of, let's say, parity? Remember that parity had just one Fourier coefficient, which was non-zero. So support has only one element.
It's one.
It's one, right? That's the only thing. In the only one vector in the support. So the span also actually just contains that vector in 0 and the dimension is 1.
Rajat, what's that character next to sparsity? So you're going to use that later on, right? Is it K?
This is K subscript F. That's my bad handwriting. That's so.
Okay, so sparsity will be K of F.
Yeah, so sparsity will be used as K, and F shows that I'm talking about function F. Okay. And looking at what we have been doing till now, probably the question is, can we relate rank and sparsity? Can we say that if the function is Boolean, then you can't have arbitrary rank and sparsity combinations? For example, if my function was just -1, 1 to the n to r, in that case, you can actually see that I can have support to be of size n and even rank to be of size, because any set of Fourier coefficients will give rise to a function like that, right? Because I can just take the inverse Fourier transform and I can get the function, which will be in this domain. But as soon as you talk about Boolean functions, this becomes special. You can't have so what in some sense you want to say is that if the sparsity is small, then the rank should also be small. That is the kind of thing which you would like to say. And the question is, what exactly can you say? If you look at the trivial thing, then the trivial thing would be log K of F. So rank has to lie between Kf and log K. And this is true even for these functions. It is not even talking about Boolean. Right?
Can I add something here?
Sure, sure, sir.
Please talk about that. So if the range is -1 + 1, yeah. So then the Fourier transform is a polynomial with a very special property, right?
Correct.
Because if you substitute +-1 values, if you evaluate it on a +-1 to the n, it evaluates to either -1 or +1 everywhere on the hypercube. It's a polynomial with real coefficients, but it evaluates either to -1 or to +1 everywhere.
Right.
So it sort of suggests that the monomials that feature in the polynomial must have some dependencies. They cannot like take values independently. There should be some internal agreement that the overall evaluation must always be -1 or +1.
Exactly.
And this is one way of capturing this rank versus sparsity question is one way of capturing that. Like if rank is as high as sparsity, that means that like all the monomials are independent and we don't expect it to be the case. Then it will take all sorts of values. Yeah.
Right. So
we expect that if the sparsity is S, let's say, then this rank, the amount of independence must be bounded. Like there is a high amount of dependence. Yeah.
So we would expect that this should become better, right? This part of the inequality should become better, and that's what we will see. So thanks, Swagato. So yeah, so what Swagato is pointing out is that this RF equal to KF seems like a case when we have no control over the monomials. Any monomials can arise in my Fourier representation, but that definitely should not happen for a Boolean function. Then my range cannot be, I cannot force it to output -1, 1. So my monomial should have some relation between them. That's what you would expect, and hence we would expect that this could be improved. And yeah, this was improved by Swagato. So let me go to that.
So one sort of naive question over here. What about the lower bound? Is it true that you can always
Yes.
get log k?
Right. So you can have Boolean functions, and actually, AND function is an example. Because your dimension would be n, and
Yes.
and every Fourier coefficient is non-zero. So that's that. So this you cannot improve.
Right.
Right. So now this slide will start making some more sense. This useless slide. Now we are at the result part, and we know what our question is. We want to upper bound Fourier rank in terms of Fourier sparsity. Right. And so this is one example. Again, constants will be missing. I will be very lazy with my with constants here. So don't blame me for that. So yeah, so if you look at functions here, you will see that this other left hand side is definitely not going to be, cannot be improved. And it actually seems like that most of the functions which we see actually log kf and rf are similar, right? So so then the question is, can it actually happen that rf is equal to k, or can we give a better bound? Or actually, let's see, can we construct functions where rf is much bigger than log k? It turns out there is an example. This is called addressing function. I will not go into the detail of this function, what this is, in the interest of time. I guess I've already finished half of my time. But the important thing here is that for this addressing function, actually the rank is pretty high. Okay. Remember, what I knew was rank was lying between these two quantities. And for most of the functions, I was hovering around this part. R was kind of log k. For AND function, OR function, majority function, many of these. The question is, can we change this relationships significantly? Can R and K be polynomially related? One example is this addressing. Here, R of addressing is actually square root of K. It is a Boolean function, but still rank is much higher, though not K, right? And Swagato was able to prove that R was upper bounded by square root K log K. Just with this extra log K factor, this is the best function which you can get.
So maybe one specific question over here. So how is t related to n? Is it, can it be arbitrarily increased or decreased, or is it?
The input size is t plus 2 to the power t. In that case. But I wouldn't, yeah. So that is the reason why the rank could be as high as 2 to the power t.
No, so t and n. So n is, so this t is a new parameter that has been introduced, right? So can it be chosen freely of n, or is it?
No. So I'm writing the equation. N is t plus 2 to the power t.
Okay, n is 2 t plus. Okay.
But anyway, so let's not go into what this function is. I can describe it later, but that's not important. But the point is, there is a Boolean function where rank could be very high as compared to the sparsity.
Just to make sure that R can be as small as possible, and also it can be as large as order n.
It can but R for a Boolean function can be order n, right?
No. I mean, for these addressing functions.
This addressing function, yeah, the rank is n and sparsity is n square.
Sure.
So yeah, so square root k seems to be the best. For a function, we can find one function where r is actually square root k. We know that it cannot be better than square root k log k. Now you might ask, what do we do here? We improve it slightly. How do we improve it? we say that actually we can have another factor here in this upper bound, which is the fraction of inputs where f is 1. So by definition, delta is less than 1. So we introduce a new parameter, and then we say that even that remains an upper bound on the rank. R is less than square root k delta log instead of R square root k log. This is what we show. This is the result which I'm going to talk about. Notice that when I talked about this result, we did not know any tight examples here. For this result. This is a very interesting open question, whether the rank could be square root k. Can we find functions where rank is actually square root k log, or addressing function is the best? Here, on the other hand, with this delta parameter, we could show that this is actually tight. We can construct functions for which R is square root k delta log. For this talk, we will just focus on this upper bound. This R is less than equal to square root k delta log. This is what we want to worry about, how to prove this. You might say this is a small improvement, but there is another interesting dimension to it, another interesting perspective to it, which is how this improves something known as Chang's lemma, which has been used in many different places, additive combinatorics, computer science, and many other places. But what is Chang's lemma? So the R result actually improves some Chang's lemma for a special case, and I'm going to emphasize what it is. What is Chang's lemma? Given a threshold t, let's talk about sets whose Fourier coefficient is big. Okay, big means greater than 1 by t. Okay, remember support was S0. So okay, I can make it, sorry, and then this would be support of it, right? I can take things bigger and bigger. I can say that, oh, I'm only interested in higher Fourier coefficients, and then the question is, can we put bound on the dimension of the span of S of t? And Chang's lemma shows that yes, indeed, there is a relationship like that. I can change this. I can write it in terms of delta. I can say that actually Chang's lemma is a lower bound on delta, on the fraction of inputs which are -1. The kind of sparsity which Shashank wanted to define. So Chang's lemma gives you a lower bound in terms of RNQ, and R result improves it. Remember that R by log K is greater than 1. This we know because R is always bigger than log K. So then instead of square root log K, we can put R by log K whole square. And this is how Chang's lemma gets improved for the when the setting is when the threshold is equal to T. So that small improvement actually allows us to even improve Chang's lemma. But I guess let's again not worry about it and look at the proof. How can we prove this? So once again, time to just revise where we are. The question is, can we upper bound rank in terms of sparsity? That is true. We already knew R is less than square root K log K because of Swagato's result. We change it, modify it to say R is less than square root K delta log K. This has other implications. This is interesting, but let's worry about how to prove it. So any questions up to this point?
Could you perhaps go back to that slide on Chang's lemma? Just wanted to take another look at it.
Sure.
The one previous, right? The definition of yeah. Okay, so ST is this. Next slide, please. for t equal to k.
So for Boolean functions, actually, we know that every Fourier coefficient has to be bigger than 1 by k with some constants.
Oh.
So
So
then
what is k here?
K is the sparsity of the function.
Oh, okay.
Because I have a function in mind, that's why I'm skipping it everywhere. Rank of that function, k of that function, so delta of that function.
Okay.
So this everything is happening for a Boolean function.
Sure. For a sparse Boolean function, the sparsity k.
Yeah. So right. So this is true for any sparsity.
True. Yeah.
Need not be small sparsity. Should I go ahead?
Sure.
Right. So what we want to prove is that r is less than square root k delta. Let me tell you, it's a very interesting kind of a way to look at it, which is where you don't have to worry about this this definition of rank and sparsity. You can think of it as saying, if I give you the Boolean function, how many parities do you need to fix to make the function constant? This is exactly the same question as finding out the rank. It is not a difficult thing to prove, but if you don't see it, don't worry about it. You can, if you think about it, you will get it. But what we are saying is that if the sparsity is k and weight is delta, then there always exist small set of parities. So remember, there are a lot of monomials which are non-zero. Around k monomials are non-zero, but you can pick square root k delta log k parities. If you fix them, if you fix their value, then the function value becomes constant. Whatever way you fix those parities. So my function only depends on those parities. This is very much in line with what Swagato was saying, right? That if you remember, he mentioned that since the function is Boolean, we assume that monomials are in some way connected to each other. They are not, they cannot be arbitrarily independent or something. There has to be some dependence between them. This result is saying that you have k monomials which are non-zero, but you only need to fix square root k delta log k parities. And all the parities here only depend on square root k delta log k. This is what this is saying. Even though you have k non-zero monomials, there are only square root k delta log k monomials or parities on which all these monomials depend. Right, and this is what we want to now show, that given any Boolean function, I can find these parities. This is how the proof will work. It is basically fixing some standard, some set of parities. So yeah, it's not a difficult thing to kind of go back and forth between rank and this formulation, but yeah. But is this formulation clear? Is this question clear? Fix this much parities, fix small number of parities, which fixes the function. Small is square root k delta. Okay. Yeah. So remember, this is so even if previous things, some of the things were not clear to us, we will just say that if the function is Boolean, we can find a small set of parities on which all the function depends. Right? That is what we want to show. So how does it happen? How do we fix parities? I have a function. If I pick a parity, remember what was chi s1 of x? This was this monomial. I element of s1 xi. Right? So every parity is a monomial like this. And if I say that my function is fixed on this this parity, chi s1x should be equal to 1, then I get a restricted function, which is this f s1 comma 1. So I'm using a new notation. Anytime I fix some parities to a particular assignment, the resulting function is called f gamma. Okay, so every function, like start with a function. If I fix s1, there are two choices. Then I fix s2, there are again two choices. I can fix chi of s2 to be 1 or chi of s2 to be minus 1. In that sense, now I get 4 functions on the bottom. So when I say I'm fixing chi s1 x equal to 1 means I'm only worrying about inputs where chi s1 of x is equal to 1. I'm looking at a reduced set of reduced set of inputs, the inputs which satisfy this condition. On that, whatever the function is, this is called f s1 comma. Right. So gamma, yeah, so gamma could actually be a set of parities. That's the only thing. It need not be just one parity, right? And then B will be a string of a set, like B is an element of -1, 1 to size of gamma. So B is an assignment of these parities.
Yeah, exactly. I also had that. Okay.
Right? Yeah. So if you look at the bottom layer, now gamma has 2 elements. So then I have to assign two bits to these parities, right? So there are 4 combinations. Right? So yeah. So for a gamma, this graph will have 2 to the power gamma leaves, basically. Okay. And what we need to, again, in terms of what we need to show, we need to show that there exists some square root k delta log k parities. If we fix them, then all the 2 to the power gamma leaves become constant. Yeah. So the result which we want to prove is that there exists a set of square root k delta log k parities. There is a small set of parities such that if I look at this graph for that set of parities, all the to the power gamma leaves become constant. Become constant function, right? Because that is what I'm saying, that fixing the parities fixes the function. The function, where once you say that my input takes on chi s1, it has this value, chi s2 this value, then my function value is fixed. My function value only depends on these parities and nothing else, right? So this is what I want to show. Okay, so fix some gamma, get to the power gamma children, right? This is the picture. Sorry, yeah, and yeah, so need to show, to prove there exists gamma such that is less than such that so Sashank or probably Amitalok, I'm doing very badly in terms of time. I don't know, are you flexible with time, or what is, how does it work here?
I think you can take a little more. It's fine. Yeah.
Sorry?
Yeah, you can take a little more time. There's no problem. We've been interrupting you fully.
Okay. Okay. Great. So if I fix f in terms of input space, it looks like this. But what happens in the Fourier domain? Right? Let's ask this question, and that will give us move us towards the solution. Right? So if I write fx as this, every time I fix a parity, a set of parities kind of get grouped together and become a single monomial. this is something which which can be understood in terms of this linear dependence independence, that if let's say there are two monomials S1 and S2, let's say S1 plus gamma is equal to S2. Okay, plus in this group operation sense, or right, or I should say that if chi S1 of X times chi, sorry, I should not say gamma, but an element of gamma, right? If this happens, then what happens when I fix small gamma, then S1 and S2's coefficients will get combined. Right? This is what is going to happen in the Fourier domain. This is how I can get my F gamma B. I had complete support, and few of the parities will start grouping together. Each equivalence class will have just one monomial.
I'm a little unclear about this equivalence class thing. So, what?
So,
yeah, can you just maybe repeat that bit?
So, the example which I wanted to give was that, yeah. So let's say I had x1, x2, right? And x1, x2, x3. These were two monomials in the Fourier representation of F, right? And let's say I fix x3 to be 1. So let's say this was C1, this was C2. Then in the resulting function, this will happen, right? C1 plus C2 is x1, x2 multiplied by x1, x2, right? This will be the term in F of x3 is set to 1, right?
Yeah.
Right. So, and you can prove that all the monomials whose coefficient will be combined, they actually form an equivalence class. It's not hard to prove. Right? I can give you a group theoretic interpretation. You look at the parities you are fixing, you look at the group generated by them, the cosets are the equivalence classes. But that's not, but yeah, you can, if you think about it, this will make sense. You do some bit of thing, but it will be equivalence classes, and each equivalence class will have a single monomial in the bottom layer, right? So remember this picture here, I had support of F things. Here, if I look at Fourier representation of each of the leaves, every equivalence class has become a single monomial. Right? So each of these are a function on function where the number of monomials have somehow reduced. They have, if L is the number of equivalence classes, then each of these Fs, the sparsity is at most L. There are going to be at most L monomials in each of these representations. Make sense?
Yeah.
Okay. And what we know is that, so this is result by Chang et al., which says that there exists square root k delta parities such that fixing them reduces the number of equivalence classes to k by 2. Okay. In terms of my, oh sorry, let me just make the picture there only. What is it saying? It is saying that there exists some gamma which is of small size, square root k delta, such that at this level, only k by 2 monomials survive. There are only k by 2 equivalence classes. I have reduced, in some sense, my sparsity to be k by 2. Okay, the number of equivalents initially my sparsity was k. Now each of the function is picking up monomials from k by 2 monomials. Now that equivalent, the number of equivalent classes have shrunk. Here the number of monomials were k. Here the number of monomials, the union of the support, at this level is just k by 2. Okay, this is lemma by Chang et al, which was proved in the previous work. Let's assume that, right? If you look at this lemma, a technique which will come to your mind is, oh, let's apply Chang's lemma to f. I will get square root k delta. I will fix square root k delta parities. My sparsity becomes k by 2. Once again, apply Chang's lemma, square root k delta by 2, and so on. And pretty soon, I will find all my functions will become constant. My sparsity, my number of equivalence classes will reduce to 1. Apply kind of inductive argument. But this will not work. This is not the right approach. The reason is that you can apply Chang's lemma only on a Boolean function. If you look at this graph, yes, it is right that the union of support here is k by 2, but I can't say that support of any one function here is k by 2. If that was there, then I could have just applied Chang's lemma to that function. The point is, yes, it is true. At this level, there are only k by 2 monomials, but they do not match to any Boolean. So I can't apply Chang's lemma here. What I need is that, so what I need to prove is that there exists a nice function here. So, right, so let me just go forward. Yeah, so need to fix parities. My strategy is going to be just, I always find, you remember that at point, I have some gamma, I have these functions. The union is not, if union of these things is big, then I can always find a function f here, which I can fix and make a lot of progress. I can reduce the sparsity by a lot. That is the essential idea. Let me just, so algorithm is going to be very, very simple. Okay, I have set of parities fixed at some point. I have these many f's 2 to the mod gamma restricted after fixing gamma to b. I should just pick a nice f and apply Chang's lemma. That would be my strategy. That will work. I have to define what nice is. Okay, that's the that's how we do it. The algorithm becomes very, very simple. Start with gamma being 5. You have a single function. You apply Chang's lemma. At every step, you have fixed some parities. You apply Chang's lemma on a nice f gamma b and update your gamma. That's the point. So and then everything happens. The termination happens when all f gamma b are constant. This is the simplest algorithm you would think of. The important point is that you can kind of find a nice f gamma b. This is the trick. This is what you need to show, that at every step you will be able to find an f. Remember again the picture. You had f. You had a lot of these f gamma b's. There exists at least one where applying Chang's lemma will give us a lot of progress. This is what we want to show. And that is our main lemma, which says that if the number of equivalence classes are big, if the union of the support is big, then I can find an f here, which will make a lot of progress. it will have big sparsity, then I can just fix this much parities, and again root k of nice f, sorry, and then I get rid of these variables. This is the argument. So algorithm is very simple. Greedily, you apply Chang's lemma. At every point, you find a nice restricted function to apply Chang's lemma. And then you stop when all f gamma b's become constant. That's what you wanted to do. It turns out that at every step, you can find a nice f gamma b. This is our main lemma. Okay, I don't think I have time to go into the calculations, but this is what it says. So I have written it in terms of the like in an inverse way, but if I reverse the equality, it will say that when L, the number of equivalence classes, is big, then the sparsity is also big. This is what it will say. So it will say that k by delta is more than, so this is for nice f. There exists a function for which this happens. So it is more than L square by k delta. So if L is big, if I still have a lot of monomials remaining, which I haven't grouped together, then there exists a function which will once again make a lot of and yeah, this proves the, I think.
So Rajat, one question here. So when you say that there exists a function, so do you explicitly give a way of constructing that function at every step?
You are saying, oh,
The nice.
You can yeah. So like I'm not doing it algorithmically nicely. I'm just saying that, oh, it's an optimization problem. You want to maximize k by delta. So a trivial way would be that you.
Yeah, after that step where you get these individual children, you said you can't directly apply Chang's. You have to show the existence of one such function. So I'm just trying to. So at this point, are you so are you looking to construct a function explicitly, or you want to show the just existence is good enough?
For us, just the existence is good enough.
Okay.
And the way to find it out, if you have a lot of time, is to actually calculate k by delta for each of the individual functions.
Okay.
And pick one which maximizes it.
Okay. Yeah.
Okay, but obviously that's expensive.
Sure.
So it depends on where we want to give a upper bound, right? So we don't care about time.
Okay.
But if you want to give time bound, then you would have to worry about how much, right? So this algorithm, we don't care about the running time of this algorithm, right?
Thanks.
Okay, yeah. So so it turns out, yeah, you can prove the main lemma. It's not difficult. I'm already like 10 minutes ahead of what I should have used, but yeah. So yeah, I use uncertainty principle, but anyway, yeah. So let me conclude. Take home message. We know that for a Boolean function, the Fourier spectrum is much more constrained. It has nice structure. We prove one more such structure. We say that rank is bounded by square root k delta. This is the take home message for this stuff. That your, as Swagato pointed out, you cannot have arbitrary independence between the monomials. If your range is -1, 1, if your function is -1, 1 to the n to -1, 1, then the non-zero monomials should be highly dependent.
So Rajat, one question about why this specific parameter delta. So when you were, so the original bound that you had as a reference point was just independent of the delta. So when you obviously were looking for some characteristic of the function which could be used to tighten the bound. So why delta first of all, and if for example you had to further strengthen it, what would be, I mean, what other things would you look for in a function? Again, I mean,
so delta, one of the reasons for delta was Chang's lemma. the reason because when we are comparing these, Chang's lemma gives a bound on rank in terms of delta.
Okay. Yes. Yes.
Right. Right. So then we say that now we already have two bounds on rank. One is square root k log k. One is because of Chang's lemma. So can we strengthen Chang's lemma? It turns out that we can, and it becomes very, very close to what it actually, it improves in some sense the square root k log k.
Okay. Okay.
So that is the reason. And other parameters here which can be useful, Swagato, I don't know, what other parameters we can.
Nothing off the top of my head.
Yeah, so actually the interesting question is this: without delta, can you make it square root k? Can you prove square root k bound, or can you give a function such that the rank is square root k log?
So another strengthening of this that one may think of is whether you can replace square root k delta is an upper bound on the Fourier L1 norm, the sum of the coefficients. So can you actually replace square root k delta by the Fourier L1 norm? Yeah, I don't know of a counterexample, but that will be interesting.
Sorry,
Fourier
R is
L1
less
norm
than
is
Fourier 1 norm.
Yeah, just the sum of the absolute values of the coefficients.
okay.
Yeah.
Very good.
So now that is at most square root k delta. Yeah, that is that follows from elementary principles. Yeah. Now, yeah. So I remember we had earlier we had initially conjectured that R is at most L1 norm times log k. Yeah.
So this is
And we could
Fourier norm, I should say.
Yeah. Huh? Yeah. So
See.
this is what Rajat just wrote is what we conjectured, and we could not prove it. Yeah. So these conjecture arose in another context about like learning Fourier sparse functions, quantum learning of Fourier sparse functions. But we did not prove it, but we ended up proving a weakening of this, which is what is written on the left. The main theorem that Rajat presented today.
Okay. Thanks. Yeah.
Okay, yeah, so this I have already mentioned that this improves Chang's lemma, and we actually show that in this case, for almost all values of R and K, you can construct a function f if that delta is actually of that order. So this is tight also. And implications are there again. Yeah, but one of the question would be that how to improve. So one of the things would be, can we improve square root k log k to square root k? We use similar techniques. So notice these three facts. We prove tight functions for this bound. That means we can't improve this, right? Since we prove tight functions, we can't improve this, but we are using similar techniques as Swagato. That means if you want to improve square root k log k bound, then very weakly saying, very intuitively saying, we need some new techniques. So that is also one side effect of this result. So again, this is yeah. So it's intuitive level. It is saying that since the same technique, if by using the same technique you come up with square root k bound, then we should be able to prove R is less than square root k delta. But that's not true. So yeah. So you require some new techniques to come up with square root.
So what is the best known lower bound that you have? I mean, in the sense that
function, right?
how large can R be? Can you?
Yeah, addressing function, right? Root k.
So you don't know of anything better than that.
No. So yeah, or so either you prove root k upper bound, or you show a function which is better than addressing,
Correct.
which improves root k. Yeah. Either would be very interesting.
But if you compare to like square root k delta, so if you have how close can you get to square root k delta log k?
Sorry.
I guess.
How? how close you can get to square root k delta log k.
Yeah, so if you have a function,
Like,
so among functions of
constant factors you can
fraction, sorry?
For up to constants, you can get a function for which r is square root k delta log k.
Oh, okay. So you can get to square root k delta log k.
Right. Right. But for all these functions, my delta is small o of 1. So that would not give you any
Okay.
counter example of r square root k log k.
Okay. So for constant delta, you still can't get
So-
close to square root k delta log k.
That would have answered the question.
Yeah. Right.
That would have closed. Yeah. Yeah. So the take-home message, as all like we already know, Boolean functions are special. One of the thing is that the rank cannot be very high if you have a given sparsity and delta. Specifically, r is less than square root k delta. Open questions. This is Swagato's work. Can that be changed to square root k, or can we find a counter example and push rank to be square root k log k? That remains open. And Chang's lemma, I talked about just one threshold. Actually, in our paper, we look at more thresholds and kind of improve Chang's lemma for more of these thresholds. And there are other thresholds to consider, but anyway, I did not go into the details, so let's not worry about it. But yeah, many more questions to look at. Yeah. So
maybe one more
finish with-
question. Like, I mean, do people look at Boolean functions on like arbitrary abelian groups, and are there sort of similar sparsity results known for those? So if you have, if you look at an arbitrary, so if you look at the class of functions on so you have an abelian group, and look at the set of functions from G to R, sorry, G to -1, 1. Right? So can you, I mean, is it interesting to study the sparsity of the Fourier sparsity of such functions?
So when you say G, you mean like you what kind of groups do you have in mind?
Any finite abelian group.
Any finite.
So in this case, it's f2, yeah, f2 to the n, right?
G is f to the power.
Yeah. So if I have a more general abelian group, can I mean, do people look at objects of this nature, and is it interesting? Can you say something about it? Because even here you do have, I mean, so the Fourier transform can't be arbitrary, right? Because f is still restricted to lie in -1, 1.
Right. Yeah. So the Chang's lemma statement is actually quite general.
Okay.
Right. So
So does Chang's lemma hold for functions of over arbitrary groups, or is it restricted
yes,
to the Boolean hypercube?
No. Chang's lemma is actually general. It works for finite abelian groups.
Okay.
But I'm not very sure whether, well, like, what is the range there? If it is the like if it is like g to the power n to g and then something like that, or
Yeah.
so yes. So I have to look for the reference and look for Chang's lemma in general, but
So I think Chang's lemma is for functions of the form g to 0, 1, something.
yeah. So that would actually
range
give
function for-
that will answer this question.
Okay.
So
Yeah, I think this is an
so
interesting
then it
question.
will,
Yeah.
yeah.
Sorry. Yeah.
So Chang's lemma will actually answer exactly this question, right?
Yeah, but it may not answer optimally. So we are looking for the relation between
Correct.
sparsity and. Yeah, I think this question can certainly be asked for more general groups. For instance, f3 to the n. Yeah, that's still a vector space. So I can the characters will reside in a vector space. So I can talk about dimension spanned by sets of characters. So rank is well defined. So this question is probably still makes sense there. I do not know what the answer is though.
Okay.
I guess.
So thank you, Rajat. I mean, I really enjoyed the talk. I've had prior experience with a bit of Fourier analysis. I was already making notes for me to refer later. Thanks for it was a very accessible talk, and thanks for dumbing down a lot of things which I perhaps have been straightforward for you.
Yeah.
And yeah, we enjoyed your talk. It was a very nice talk. It was a different talk from the previous ones you've had in the sense of it felt more like a class, and that's what made it more enjoyable as well. And thank you for accepting our invitation and being here.
Yeah. Sorry for taking more time than.
No worries. Thanks for being patient with all my questions.
No. That was.
Yeah, so you can see the fact that questions kept coming throughout the talk means it was, we found it very accessible and it was very interesting, certainly.
Okay. Thank you. Thanks a lot for the invitation.
Yeah, thank you very much. So nice. Yeah, I hope we can meet again. Hopefully in Kharagpur, if not, then somewhere. Yeah.
Yes, definitely. Swagato, you.
Swagato is the interview, so he's going to keep us informed if he ever come down here again.